Welcome to our lecture video in hydraulics with the topic branching pipe reservoirs at different elevations, the 4 reservoir problems. In this video, we will answer the 3 sample problems in this handout. So in these 4 reservoir problems, we have case 1 and case 2. So for case 1, in this 4 reservoir A, B, C, D, the reservoir A will have a flow from the reservoir up to the junction here. Say this is junction X. And this junction X, the flow of water is from junction X towards reservoir B. Now if that happens, the piezometer reading is above the elevation of the reservoir B. Whereas we have case number 2 here, the highest reservoir A and the next highest reservoir B will have a flow from this reservoir up to the junction X. So since they will share the flow here, they will merge the flow in this junction, we will find that the piezometer reading here is lower than the elevation of reservoir B. And then we will derive different equations based from these 2 cases. So let's use these 2 cases in solving the 3 sample problems from this handout. So we have example number 1, reservoir A at elevation 90 meters above datum furnishes water to a 600 mm pipe, or that will be a 600 mm diameter pipe, which leads to a point at elevation 30 meters, the pipe being 600 meters long. Here, it branches into 3 pipes, the 200 mm diameter, 300 mm diameter, and 100 mm diameter. The 200 mm pipe runs 300 meters and discharges to reservoir B at elevation 75 meters. The 300 mm pipe runs 450 meters to reservoir C at elevation 52.5 meters. And the 150 mm pipe runs 900 meters and discharges to reservoir D at elevation 30 meters. Friction factor F is equal to 0.02 in all pipes. Compute letter A, the discharge from B, discharge from C, and C discharge from D. So we have 4 reservoirs A, B, C, D, given the elevations of this reservoir being the reservoir A is 90 meters, the reservoir B has elevation 75 meters, the reservoir C has elevation 52 meters, and reservoir B has elevation of 30 meters. And given the diameters and the meter or the length of the pipe, so we can have this drawing here. So we have the 90 meters for A, 75 for B, 30 for D, and 52.5 for the reservoir C. And this is the summary of the pipe length, the length, the diameter, and the friction factor F based on the problem. So it would be easier for us to solve the problem if it is summarized this way. So usually the problem will be like this in a worded form, but the tabulated form will help us to solve faster. Okay, so from this drawing, what can we derive here? It says there that, so obviously the water from elevation A being the highest, it will flow from the reservoir A up to the junction P. So let's name this junction P. So it says here reservoir A at elevation 90 meters above datum furnishes water to a 600 mm pipe which leads to a point at elevation 30 meters. That's why we have elevation of 30 here. This is the point from A to elevation 30. Next, it says here the pipe. So given the pipe is 600 meters long. So that's why we have 600 meters length for pipe 1. Here, so from here, it says from this junction, it branches into 3 pipes. The 200, 300, and 150 mm diameter pipes. As for the 200 mm pipe, given the 300 meter, discharges to, it says there, it discharges to reservoir B. So from the word to, we can say that the flow is from P to reservoir B. So the flow is upward like this. And then the 300 mm pipe runs 400 meters. Again, the word is to reservoir C. So this is the flow of water to reservoir C. And the 150 mm pipe runs 900 meters and discharges to reservoir D. So we have here the flow of water from P to D. So having this flow of water, this is in case number, so that will be in case number 1, wherein Q1 is equal to Q2, Q3, and Q4, being the pipes 1, 2, 3, and 4. So let's name this also as pipe 1, 2, 3, and 4. So we need to be consistent as to the worded problem for reservoir D. So the pipe from the junction P to reservoir D, it is 150 mm in diameter and 900 meters in length. So we have here for pipe 4, we have 150 and 900 meter length. So it should be consistent. So let's draw the head, so for HB, HC, and then this would be the HD. So this is HB, this is HC, and then this is HD. Now, having the case 1, the piezometer reading is above the elevation of reservoir B. So we have here the piezometer P as above B. So it will be located around here. Let's say here. Piezometer P. Therefore, the HF1 and then for the HF2 and HF3, so let's see. So this is our HF1. Then we have the HF2 here. the HF3. And the HF4. So these are the heads. Okay, so since this is case 1, wherein Q1 is equal to Q2 plus Q3 plus Q4. And this is our equation number 1. Next, our HB here, which is what is 90 minus 75, that is 15. So HB is equal to, that will be HF1 plus HF2. So as you can see here, HF1 plus HF2, that will be your HB. And that is equal to 15 meters. And that is our equation number 2. Next is the HC. HC is this one here. And that is equal to HF1 plus HF3. And that is our HC. So HF1 plus HF3. And this is equal to, since we have elevation, so what is 90 minus 52.5? So 90 minus 52.5 is 37.5. So this is 37.5. Equation number 3. Next, we have HD. So our HD here is HF1 plus HF4. So HF1 plus HF4, and that is equal to, since given the elevation of D, so what is 90 minus 30, that is equal to 60. So that is equation number 4. Now, since we're using friction factor F, our formula for HF is equal to 0.0826 FLQ squared all over be D raised to 5. So we will, so how do we get here the value for QB? So we will use the equation number 1 here, wherein in this formula we will have the value for Q is equal to square root of HF D raised to 5 all over 0.0826 FL. So we will use this Q and substitute it here. Since we have the values for HB, HC, and HD already, so we can get the value for Q here. So all of them had HF1. So let's have HF2 in terms of HF1. This is 15 minus HF1. So HF3 is equal to 37.5 minus HF1. And then HF4 is equal to 60 minus HF1. Now at 1, wherein Q1 is equal to Q2 plus Q3 plus Q4, we will use this formula. So since all the pipes have same coefficient constant here and coefficient or friction factor F we will remove 0.0826 and F. So for Q1, that is square root of HF1 times the diameter for Q1 is 600 and the length is 600. So 0.6 raised to 5 for the diameter all over the length is 600 meters equals for Q2. For Q2 we have square root of HF2. Now HF2 here is 15 minus HF1. So 15 minus HF1, diameter and length for pipe 2, diameter is 200, length is 300. Diameter 0.2 raised to 5 and then 300 length. So plus square root of, so for Q3 we have HF3. HF3 is equal to 37.5 minus HF1. Diameter and length for pipe 3 we have 300 and 450. So this is 0.3 raised to 5 and length of 450 plus for Q4 we have HF4 60 minus HF1. So we have here 60 minus HF1. Diameter and length for pipe 4 we have 150 and 900. So 150, so 0.15 raised to 5 all over 900. So we can solve this using the shift solve function of our calculator. To get the value for HF1. So square root of alpha x times 0.6 raised to 5, 600. Alpha equals square root of 15 minus alpha x 0.2 raised to 5 over 300 plus square root of 37.5 minus alpha x times 0.3 raised to 5, 0.3 raised to 5 all over 450 plus square root of 60 minus alpha x times 0.15 raised to 5 all over 900. Shift solve. So x, or that is HF1, is 2.92. 2.92 meters for HF1. So having the value of HF1, we can now get the values for Q1, QB. QB being the Q2, QC being the Q3, and QD being the Q4. So we can now get these values for letter A for Q2. So this is our Q2. We just add the 0.86 FL that we cancelled a while ago. Okay, so that is equal to square root of 15 minus 2.92 times 0.2 raised to 5 all over 0.0826. F is 0.02, L is 300. So Q2 is equal to 15 minus 2.92 times 0.2 raised to 5 all over 0.0826 times 0.02 times 300. So 0.088. So Q2 is 0.088 cubic meter per second. Next, let's go to B for Q3. So this is the Q3. So that is equal to square root of 37.5 minus 2.92 times 0.3 raised to 5 all over 0.0826 times 0.02 times 450. So that is equal to 37.5.3 and then 450. So 0.336 cubic meter per second. 0.336 cubic meter per second. Next, for letter C, we need to find Q4. Q4 is this one here. So square root of 60 minus 2.92 times 0.15 raised to 5 all over 0.0826 0.02 times 900. That is equal to 0.15 and then 900. 0.054 cubic meter per second. So that's number 1. So if you're struggling with the shift solve in this portion here, there's a struggle for a shift solve there. All you need to do is to reduce these into smaller value, to reduce them, and then you can solve them algebraically, or you can input them again in the shift solve function but in a simpler form. Next, we have here number 2, reservoirs A and B. So reservoir A and B are supplying water to 2 newly created town sites. So there are 2 newly created town sites that these 2 reservoirs will supply water. So from that condition itself, that means since they are supplying the 2 town sites here, therefore the flow of water is towards the junction, since they are supplying, they're both supplying. Elevation of reservoir A is 240 meters, and it says there it is 12 meters higher than reservoir B. Therefore, we can now put here that HB is equal to 12. Since it says there it is 12 meters higher, the reservoir A is 12 meters higher than reservoir B. So HB is equal to 12 meters. From A 450 mm diameter pipeline, 1,350 meters long, connects the reservoir to a junction point C. So this is the junction point C. Therefore, this 450 mm diameter pipeline and 1,350 meters long is for the pipe number 1. So let's name this as pipe 1. And let's name this as pipe 2. This one here as pipe 3, and this one is 4. So as you can see, we summarize it in the table below. So that's the diameter and length of pipe number 1. Now how about B? Another 450 mm diameter pipe, 1,500 meters long, is connected from C to reservoir B. So the connection, the word here to signifies to the connection of the pipeline, but not the flow of water. So as you can observe the previous example, we understood the word to as the flow of water. So it says here, discharges. The word here, discharges to. And then discharges to. So it means it refers to the flow. Whereas here, the word 1,500 meters long is connected from C to reservoir B pertains to the connection of the pipes only and not the flow of water. So at this junction C, a 300 mm diameter pipeline, 2,400 meters long, is laid out towards the new Townsite D at elevation 150 meters. So from C to D, let's name that as the pipeline number 3. So 2,400 meters length, and the diameter of the pipe is 300 mm. Given also the elevation of 159 meters. Then another pipeline, says here, another pipeline, 300 mm diameter, 1,800 meters long, is installed towards the new Townsite E at elevation 150 meters. So again, that is another pipeline from C towards E, and given the elevation of 150 and its diameter of 300, so diameter of 300 and length of 1,800. So friction factor, they all have the same friction factor of 0.02. So compute, it says there, compute for letter A, compute the rate of flow, which is the Q, in pipe connecting junction C to reservoir B. So what pipe is that? Connecting junction C to reservoir B. That is the pipe number 2. So we are looking for Q2. Now for letter B, how many person is supplied per day in Townsite D? So here, Townsite D, if each person consumes 0.38 cubic meter per day. How about in Townsite E? So we're going to solve for the Q of pipe 3 and pipe 4 in order to solve for the number of persons to be supplied in those two town sites. So since the flow is like this, and the flow from junction C, since the town sites are being supplied, so it will be this flow, so away from junction C. So this flow here is actually case number 2. So for the case number 2, the piezometer reading is below the elevation of B. So the piezometer reading here is below B. Therefore, this is our location for P. So this is our P now. So we already have HB here. So how about the others? So HE, this is for the HD. HD, this is HE. So this is HI. E. Since the elevation is given, so what is HE? So that is 240 minus 150, that is 90. HE is equal to 90. How about here? From elevation A to elevation of Townsite D. So HD is equal to 240 minus 159, so that is 81. So 81. Okay. Then for HFs, for the HF, okay. So this is our HF1. HF1. For our HF2, this is our HF3. For pipelines 3, so HF3. Then this is our HF4 here. So what other relationship can we see here? The relationship of the elevation B to D. So we have here elevation B to D, that is so that is 240 minus 12 minus 159, so that is 69. This one here is 69 meters. And what else? This one here. So this measurement here is actually 240 minus 12 minus the elevation of E minus 150. That is 78 meters. Yes, I think we're complete already. So for this being our case 2, what can we see from the case 2? Case 2 is Q1 plus Q2 is equal to Q3 plus Q4. So this is what we have here. In our problem, we have Q1 plus Q2 equals Q3 plus Q4. This is our equation number 1. Now how about HB? For our HB, that is equal to HF1 minus HF2. This is our HF2. To get the value for HB. So HF1 minus HF2, and that is equal to 12. That is our equation number 2. HD, so HD here, which is 81, is equal to HF1 plus HF3. So that is HF1 plus HF3 equals 81. Next, we have HE. So this is HE is equal to 90. So that is equal to HF1 plus HF4. So HF1 plus HF4 equals 90. Equation number 4. Since we're using here friction factor F, therefore our HF is equal to 0.0826 FLQ squared all over D raised to 5. And we will be using Q is equal to square root of HF D raised to 5 over 0.0826 FL here, FL. So using the relationship at equation 1, let's get all values of HF2, 3, and 4 in terms of HF1. So here we can have HF2 is equal to HF1 plus, or that is minus 12. Then HF3 is equal to 81 minus HF1. HF4 is equal to 90 minus HF1. Then, at equation number 1, being Q1 plus Q2 equals Q3 plus Q4. Now for Q1, that is square root of HF1. The diameter of pipe 1 is 450, length 1350. So 0.45 raised to 5. And then since they have this same constant and this same friction factor, we can cancel it out. So what's left is the length, 1350. Next, plus square root of Q. So for Q2, we have square root of HF2. HF2 being HF1 minus 12. HF1 minus 12 times the diameter for 2 is 450, length 15. 0.45 raised to 5, then length of 15. That is equal to Q3. So for Q3, that is square root of, so HF 81 minus HF1. So 81 minus HF1. Diameter for pipe 3 is 300 and length is 24. So 0.3 raised to 5. Then length is 2,400. Then plus Q4. Q4 is square root of HF4. HF4 is 90 minus HF1. So 90 minus HF1, diameter and length for pipe 4 is 318. So that is 0.3 raised to 5 all over 1,800. So HF1 using shift solve now is equal to square root of alpha x 0.45 raised to 5 all over 1350 plus square root of alpha x minus 12 times 0.45 raised to 5 all over 1,500 equals, so alpha equals square root of 81 minus alpha x times 0.3 raised to 5 all over 2,400 equals, plus. So plus square root of 90 minus alpha x times 0.3 raised to 5 all over 1,800. So shift solve. So for HF1, that is 13.77. So 13.77 meters. So what are we looking for here? For letter A, compute for Q2. So for Q2, we have this one here. So, and then we will input the 0.0826 and 0.02. So Q2 is equal to square root of HF1 13.77 minus 12 times 0.45 raised to 5 all over 0.0826.02 times 1/5. So what's our Q2? That is square root of 13.77 minus 12 times 0.45 raised to 5 all over 0.0826 times 0.02 times 1/5. So that is 0.115. 0.115 cubic meter per second. So we get a positive value. That means our assumption is correct. The assumption that the water is flowing from B to the junction C. Next, for letter B, how many person is supplied per day in Townsite D if each person consumes 0.38 cubic meter per day? How about Townsite E? So here we are required to find the values of Q for Townsite D and Townsite E. So we're looking for Q3 and Q4. Let's solve the Q3 and Q4 for B and C. So for B and C, let's find Q3 and Q4. Q3 here is this one. This is square root of 81 minus 13.77 times 0.3 raised to 5 all over 0.0826 times 0.02 times 2,400. So what's the value of Q3? So that is 81. 81 minus 13.77 0.3 and then 24. So Q3 is 0.203. 0.203 cubic meter per second. How about Q4? So this is the Q4. For Q4, that is square root of 90 minus 13.77 times 0.3 raised to 5 all over 0.0826 times 0.02 times 1,800. That is equal to, so that is 90 minus 13.77, 0.3 raised to 5, 0.0826 times 0.02 times 18. So 0.249, or that is 25. 0.25 cubic meter per second. And we will use it here in B and C. To supply the number of person, we need to remember that Q is equal to volume over time. Having known this, our Q is equal to for Q3. That is Q3. So Q3 is 0.203 equals the volume here. So that is in cubic meter per second. our per person is 0.38 cubic meter per day. It says there per day. So from the condition here, each person consumes 0.38 cubic meter per day. And this is the Q being supplied in Townsite D. So if this is per person, so we will put here X for, so times X for the number of person here. But let's convert this day into seconds. So 1 day is 86,400 seconds. So 86,400 seconds in a day. Cancel day here. So X now is equal to, that is 0.203 times 86,400 seconds in a day all over 0.38. So we are going to supply 46,156 person. So 46,156 person in Townsite D. So same method here for C. For C again, we have our Q for 0.25. So 0.25 cubic meter per second is equal to 0.38 cubic meter per day, number of person X, and the conversion 1 day over 86,400 seconds. Cancel day here, cancel cubic meter per second. So what's left here for X is, so we are supplying 56,843 person. So 86,456 is 56,843. 843 person for Townsite E. So why 843? Because there's no 0.1 person. So we will round it up into the whole number. So that 0.1 there, that 0.1 person becomes 1 person. Therefore, 56,842 plus 1. So we have 56,843 person. So that's for example number 2. So let's go to the last problem, number 3. So reservoirs A, B, C, and D have elevation of 80. So for letter A, we have 80 meters elevation. For B is 90 meters elevation. C, 100 meters elevation. And D, 90 meters elevation respectively. The rate of flow from P, so this P here, to reservoir A is 515 liter per second. Reservoirs A and B connects to junction P1. So meaning the P that it mentions here is actually the P1. So that is P1. And reservoirs C and D connects to junction P2. So there are 2 junctions. That's why it looks like this. Using the properties of pipes as shown in the table, so this is the table, compute the rate of flow in liter per second and the direction of flow in pipe number 2. So it's asking for direction of flow in pipe number 2. What's pipe number 2? It's reservoir B2 P1. So reservoir B2 P1. So this is the pipe number 2. So it's looking for Q2. Then letter B, pipe number 5. Compute the rate of flow in liter per second and direction of flow in pipe number 5. So this is the pipe number 5 from reservoir C to P2. So reservoir C to P2, this is pipe number 5. So let's name the rest of the pipes. Pipe 1 is reservoir A to P1. Reservoir A to P1. So this is pipe number 1. So pipe number 1, 2. Then for pipe number 3 is P1 to P2. P1 to P2. So this is pipe number 3. Next, we have pipeline 4 is reservoir D to P2. So D to P2, this one here. This is pipe number 4. Okay, so we have named all pipes. Now it says there is a given flow, rate of flow Q. Rate of flow Q from P to reservoir A. So from P to reservoir A, this one here is 515 liter per second. Meaning, the Q1 is already given. So this is the flow of Q1. Q1 is 0.515 cubic meter per second. So that's the given. 515 liter per second is 0.515 cubic meter per second. So having given the Q1, so obviously from elevation 100 meters of reservoir C, the flow is downward. And this here is obviously, we have their downward flow. So we will need to, so this is pipe 5, this is Q5. Since for elevation 90 meters here, let's assume a flow towards D. Anyway, if the value will be negative, that means our assumption is incorrect. We will assume a value, the direction of flow here as from P2 towards D. And for this, we will assume it as from reservoir B to P1. So there goes our assumption. So what case is this? What case is this? That will be case number 1. So case number 1 here, wherein the piezometer reading is higher than elevation of B. So piezometer reading here will be higher than B. Let's use black. So let's put P here. So how about this? There are two cases. So for this is case number 1. How about at this point? This flow is towards the junction, therefore that is case number 2. Case number 2 wherein P is lower than B. So the P here is lower than this. So P will be located here. Let's name this as piezometer P, piezometer reading P. So this is our HD. So HD here is 100 minus 90. That will be, so HD is equal to 10. Now how about HB? So for HB here, this is our HB is also equal to 10. For HA, this is our HA. That is 100 minus 80, so that is 20. So HA is equal to 20. Next, we find the HF. This is pipe number 5, so this is the HF5. HF5. From this reservoir to pipe P. For HF4, from the reservoir to the pipe or the piezometer P. So this is HF4, from this elevation to piezometer P. Next, how about this one here, HF2? Where is the source of water? This, the elevation B up to piezometer P. So this is our HF. HF2. Now for HF1, so we have here from elevation of A up to piezometer P. So what else? We also have for the third pipe, pipe number 3, piezometer to piezometer. That's the HF3. So any more relationship here? So how about this one? Elevation 90, elevation 80. The difference there is 10. HF2 plus HF1 is equal to 10. Okay, so we can now derive the equations from this setup. So Q5, this Q5 here is equal to Q3 plus Q4. So Q5 is equal to Q3 plus Q4, and that is the equation number 1. Next, our Q1. Our Q1 is Q2 plus Q3. So this Q2 and Q3 will combine to form Q1. And Q1 is 0.515. So Q1 is equal to Q2 plus Q3 equals 0.515. Equation 2. Next, let's go to HA. HA. HA is equal to 20 here, and HA is equal to HA is equal to HF1 plus HF2. No, it's not HF2. So HF1, so HF1 plus HF3 plus HF5. So that's for HA. So HF1 plus HF3 plus HF5. That is equal to 20. So equation number 3. Then we see the HD. So the HD here, HD is equal to HF2 plus HF4. So HF5. So HF5 plus HF4, and that is equal to 10. So this is equation number 4. Then we have HF2 plus HF1 equals 10. So HF1 plus HF2 equals 10. That is equation 5. Since we're using friction factor F here, so our HF is equal to 0.0826 FLQ squared all over D raised to 5. So how do we get the value for Q2? So it's from here, from the equation 5. So if we get the value of HF1, we can now get the value for HF2 and solve for the Q2. Now since Q1 is already given, having Q1 is 0.515, we can now get the value for HF1. So HF1 is equal to 0.0826 F. What's the F? Here is for HF1, that is 0.025. 0.025. The length of 1 is 600, diameter 600. Length 0.6 raised to 2. Oh no. That is 600. So 600 meters. Then Q is 0.515 squared all over the diameter of 0.6 raised to 5. So HF1 is equal to 0.0826 times 0.025 times 600 times 0.515 squared all over 0.6 raised to 5. So HF1 is 4.23. 4.23 meters. Therefore, at equation 5, HF1 is 4.23. 4.23 plus HF2 equals 10. So HF2 is equal to 10 minus 4.23, 5.77. 5.77 meters. Using this value of HF2, we can now solve for Q using this formula. So 5.77 equals 0.0826. What's the F for 2? Pipe number 2. 0.03. Diameter of 450, length of 600. So 0.03. Length of 600 Q2 squared. And then the diameter of 450 or 45. 0.45 raised to 5. So what is Q2? What is the value for Q2? 5.77 times 0.45 raised to 5 all over 0.0826 times 0.03 times 600. So 0.268. So that is 0.268 cubic meter per second. And the problem says that find the rate of flow in liter per second. So that is Q2 is equal to 268 liter per second. So that is from the conversion 1000 liter in 1 cubic meter. And since the answer here is positive, therefore, and this is less than, also this is less than 0.515, therefore our answer is correct. The assumption here that is downward, it is therefore from, direction is from reservoir B towards P1. That is for letter A. Now letter B, pipe number 5. So for pipe number 5, we are already sure the direction of flow is like that, downward. But what is the value of Q? So we now have the value for Q2, so we can get the value of Q3 for equation number 2. And okay, so we can get the Q3 here, substitute here at equation 3, knowing that we have values for HF1. So we're going to use equations 2 and 3. So at equation 2, we're in Q2 plus Q3. So Q2 plus Q3 is equal to 0.515, Q2 being 0.268 plus Q3 equals 0.515. Q3 is equal to 0.515 minus 0.268, 0.247. So Q3 is 0.247 cubic meter per second. Next, at equation 3, so HF1, so at equation 3, we're in HF1 plus HF3 plus HF5 is equal to 20. Our HF3, we can solve the HF3 already. So HF3 is 0.0826. What is the F for 3? F is 0.03, diameter 450, length of 900. So 0.03, length of 900, Q of 0.247 squared all over, the diameter is 450 or 0.45 raised to 5. So HF3 is equal to 0.026 times 0.03 times 900 times 247 squared, 0.45 raised to 5. So HF3 is 7.37. Then we now have from this equation, our HF1 a while ago is 4.23. So 4.23 plus HF3 7.37 plus HF5 is equal to 20. So HF5 is equal to 20 minus 4.23 minus 7.37. Oops, 4.23. So 8.4. So HF5 is 8.4 meters. This is less than the 10 meters. So look at our HF5 here. So HF5 here is, you add it with HF4 to get 10. So since the value of HF5 is lesser than 10, therefore our assumption here that it's downward is correct. Assumption correct. So we now use 8.4 or HF5, that is equal to 0.0826. What is the F for pipe number 5? 0.03, diameter 450, length of 300. So 0.03, the length of 300, Q5 squared, and diameter of 450, 0.5 raised to 5. So Q5 is now equal to times 0.45 raised to 5 all over 0.0826 times 0.03 times 300. So 0.457. So 0.457 cubic meter per second. And 1,000 liter in every 1 cubic meter. Q5 now is equal to 457 liter per second. So that's the example number 3, our last example. Okay, so that's all for this video.